Sometimes when we try to take an integral of a function, the function is a complex combination of functions that we know how to take the integral of. So one of the tools we can use is substitution. Now, it doesn't always fall out nicely. We're going to craft very clean-cut examples in this case, but I'm going to give you some pointers of things that you might try or at least look for in order to see if the substitution method is one that you might use. We'll start by looking at an example that we know how to solve for in a different way, just so that we have a reference point to what the U substitution method should give us. And then the next few examples, we'll look at something that we don't know how to solve in a different way. So the first example, we have x plus 1 quantity squared, and we can expand that to x squared plus 2x plus 1. And we know from the previous video that we can use the additive method of integrals and break this up into individual integrals. So the integral of x squared, we know from this equation is going to be 1/3 x cubed. The integral of 2x we know is going to be, again from this equation, 2 times a quantity, 1/2 x squared, or just x squared. And then the constant 1 is going to just be x. So we take those integrals, right? There's 1/3 x cubed, there's x squared, and there's x. And then we apply the limits, lower limit 3 and upper limit 6. There's my x cubed terms, my x squared terms, and then my x terms. And we'll get an area or integral of 93 for the total function. So graphically, what does this look like? This is my x squared term. This is my 2x term, and then this is my constant 1 term. And when we add these areas together, we get the full function, the x plus 1 squared function all together. Okay, so we just did that, so we have the reference that we're expecting the answer to be 93. What's another way to look at this? Well, when we're trying to use the substitution method, try to look for things that if you made a substitution for looks similar to trig components here. You'll never do a substitution like u is equal to x, because something like that, you're just doing a direct substitution, and that doesn't help you clean up or simplify the equation at all, right? If you just do a one-to-one substitution. So don't worry about that. So the only other option is either the square component or something inside a power term. So a lot of times you'll see, and we'll see examples, if something is to a power, that whatever is to that power might be a good use of substitution. Or if it's something within a trig component, right? Let's say it's like sine to some sine x is usually what we see. But if it's sine something else, that something else might be a good substitution. Now it doesn't always work because we'll see there's an additional step than just directly substituting. But in this case, this one's pretty easy to see that x plus 1 could be one to try. Now sometimes these use substitutions for larger, more complex functions, you're going to need to do a couple trial and error before one of the substitutions makes sense to take. But we're going to start off looking at some simplified ones. So I'm going to say that u is equal to x plus 1. Now this variable u is a dummy variable. You can call it a, you can call it b, it really doesn't matter. It's a placeholder for us. Now the important thing when we do substitution in integrals is if you substitute here, you have to substitute for what you're taking the derivative of, and you need to substitute what your limits are. Okay, so it's really easy to forget about your limits and to update those. Take the integral, substitute these into that, and then you're definitely going to be inputting the incorrect limits, right? Because these limits here are for x equals 3 and x equals 6. They do not directly relate to the new substitution variable u. Okay, so the first thing is you pick something that you want to substitute. In this case, I say x plus 1 is equal to u. Then you need to think about how this dx term will change, because you can't have dx if you're trying to integrate something with respect to u. So you solve for du. So in this case, du is equal to dx. Now, what's the thought process here? You could say, what is du dx? In the same way that you took a derivative of y is equal to x plus 1, you could say dy dx is equal to 1. But we're not trying to solve for a dy dx or du dx form. What we're trying to solve for is the relationship between du and dx. So the change in u is equal to the change in this component. This is a variable x, this is a constant, so that's going to drop out. If this at all, the notation is funky to you, just write it as this is like a y term, right? I know sometimes just changing the variable letters can be confusing. So if you want to call this y, feel free to. But in this case, I'll just call it u here. If I say du dx, I can solve for this, and this will be 1. And then I can move the dx part over to the right. That's essentially what we're doing. Okay, so I have my u substitution. I have my du substitution, or my dx substitution, however you want to look at it. Next thing is I want to write my limit substitution. So I have a lower limit of x equals 3, upper limit of x equals 6. So I need to substitute that. All you're doing there is plugging the lower limit into the substitution and replacing that with a u lower limit substitution. So at x equals 3, we plug in 3 here, 3 plus 1, we get a lower limit of u equals 4. And we plug in x equals 6 here, we get 6 plus 1, u is equal to 7. So when I take the this form of the function integral, and then I'll substitute with my u values, my du values, and my lower and upper u limits. So ignore this for now. Let's focus on this term right here. So x plus 1 squared is going to be replaced with u squared. Dx is going to be replaced with du. The lower limit 3 for x is going to be replaced with u lower limit u equals 4. Upper limit x equals 6 is going to be replaced with upper limit u equals 7. Right? And so now this is the new form I'm going to solve for. U squared, I can use this equation again to solve for it. U squared is essentially x squared, right? With these new limits. Then you get 1/3 u cubed, because n is equal to 2. And then we have our limits 7 and 4. So 1/3 upper limit 7 cubed minus lower limit 4 cubed equals 93. And this graph here is as a function of u instead of a function of x. And this is u squared, the integral of it from 4 to 7. And this area here is exactly equal to this one. They're both 93. So I'll repeat the steps quickly. First, we look at the function, see what possibly can be substituted. We test one of them out. We say u is equal to x plus 1. We solve for the relationship between du and dx. We solve for the lower and upper limits in terms of the substitution variable. And then we make the substitutions of the integral with all u terms. We don't want any x terms. We don't want the limit to be in x. We don't want the dx component to be there. We don't want any x terms to be in here. Substitute all into our substitution variable u, and then we integrate. And then we solve for that problem as if it was a brand new problem, and we'll get the same integral area if we're doing it correctly. So let's take a look at another problem that we may not know the exact answer, but we're going to follow these same exact steps. For our next problem, we have the integral of sine 5x. I know how to take the integral of sine x, but I don't know how to take the integral of sine 5x. So that's a probably good indication that 5x would be a good place to start and see if that's something that we can use u substitution for. All right. If I graphed sine 5x, I would see this with my lower and upper limits of pi to 2 pi. I see there would be terms that I expect to cancel. And so I can, if I wanted to, equate it to just this small section. But at least I know I should expect to see a negative value here. Let's take a look. All right. So we're going to start with the substitution. u equals 5x. And we're not confident that this is going to work, but this is a good first guess. And then I need to find a relationship between du and dx. So I can make that substitution right there, right? So du dx here would be the derivative of 5x, which would just be 5. So I can rewrite that as du is equal to 5 dx. Okay, that looks like it works pretty well. And what am I checking for? I'm checking for any extraneous terms. If it's just a constant in front, that's actually pretty clean. We'll see in future examples when there is no constant in front, actually that it works in certain circumstances. Again, remember your limits need to be changed into the new substitution variable. So I need to write x equals pi in terms of u. And I need to write x equals 2 pi in terms of u. So pause this video and see if you can figure out what the limits would be in terms of u. Okay, so hopefully you figured it out. Remember, all you need to do is plug in these x lower and upper limits into this equation, and you would get your upper and lower u limits. So at x equals pi, I get u is equal to 5 pi just by plugging in x equals pi into x, the x variable term here. X equals 2 pi, you plug it in here, you should get u equals 10 pi, right? It's as simple as that. Okay, now we have to rewrite this equation in terms of our u limits and derivative functions and function itself, okay? So focus on this first term right now. So the lower and upper limits are changed to 5 pi and 10 pi. That's what this is here. I substitute 5x with u. That's what this sine u comes out as. And I substitute dx with this portion here. So if I isolate dx, I move the 5 to the left side, I get 1/5 du, right? So hopefully make sure that substitutions all make sense. All right, so 1/5 is just a constant, so I can pull that out of the integral, and it's just going to be sine u du, the integral of sine u du. Oh, I know what that is. I have that right here, negative cosine. So I have 1/5 times negative cosine u, and we need to apply the limits 5 pi to 10 pi. So I'll pull this negative sign out. I get negative 1/5 cosine 10 pi. Cosine 10 pi. 10 pi is a multiple of 2 pi, right? So remember the unit circle goes from 0 all the way to 2 pi, and it just is repeating at that point. So cosine of 10 pi is the same thing as cosine of 0 or cosine of 2 pi. So that's the positive x-axis. So that is positive 1 for cosine. Minus the lower limit, cosine at 5 pi. 2 pi is not a multiple of it. It's actually, right, so if you go 2 pi, that's one loop. 4 pi, that's the second loop. And then you have pi, one more pi to get to 5 pi, right? So that means cosine of 5 pi is equivalent to cosine of pi. And what's cosine of pi? Cosine of pi is what's the x value along the negative x-axis. So that's the 180 degrees, right? So that's negative 1, right? The negative x-axis. So 1 is upper limit minus the lower limit is negative 1. So 1 plus 1 is 2. Negative 2/5, we have negative 0.4 as my final solution. And if I graph the function 1/5 sine u, this function right here, after we do the substitution, right? So then y versus u, we see the integral from 5 pi to 10 pi. And again, it's just that one section right there. Okay, so what do? We tested out u substitution, figure out du, and apply the limits, right? So next set, it's going to be the same thing, just a little bit more complex form, but it's the same process over and over. We're going to continue looking at different examples of substitution. Here we have x e to the negative x squared. Definitely doesn't show up in that exact form in our table. So what do we need to look at? Well, we have an x term here. A u substitution with x is not going to do us any good, remember, because just now we're going to have that single variable. A one-to-one substitution doesn't work for us. And we have e to the negative x squared. So maybe I substitute u is equal to e to negative x squared. That's possible. I have e to the negative x squared. I could, there's a small term right here, x squared. Maybe I could substitute for x squared. So that's going to be the one I first start with. I'm going to start with u is equal to x squared. Let's see what we get. So this is the actual graph of x equal to x times e to the negative x squared. And then the shaded area is the integral with limits 0.5 to 1.5. Okay, so we're expecting to see a positive integral from this example. All right, so let's try u equals x squared. So if we plug in u equals x squared, I need to find, after I have this, my du dx relationship. So press pause, see if you can figure out what the relationship between du and dx is. And remember, if you don't understand that going directly, solve du dx first, and then manipulate it so that it's a du is equal to something dx. All right, so hopefully you recognize this as 2x dx. So du is equals 2x dx. Now, does that work? Now, it doesn't fall out cleanly as just a constant in front like we saw in the other examples. But this x actually helps us out because you have an extra x term out here. Okay, so we're going to continue trying this. And if we look at the limits, I have x equals 1/2 and x equals 1/2. We just plug it into this equation, right? So the lower limit, x equals 1/2, plug it in. So 1/2 squared gives me 1/4 for u, the lower limit of u. The upper limit, 1.5, plug that in. I get the upper limit of u is equal to 2.25. Okay, so now let's try to plug in to this equation. There's a couple ways to do it. I think I went around actually the longer way, but it might be clearer or more direct. So what I did is I plugged in u for this x squared, right? That was the initiative to even consider this u substitution. So that's what this e to the negative u term represents here. I don't want this x term to show up here, but I'm going to leave it there for now and see if it falls out. Of course, I know that it will because I designed this problem, but if you didn't know, that's what you could do. That's one method of looking at this. So then the next thing is that you have a dx term here, so you can write du divided by 2x equals dx, right? And that's this substitution right there. Okay, then you have an x here and x here, so those will cancel out. And before we move on to the next step, then we do our substitution for our lower and upper limits. And so instead of x equals 0.5 and x equals 1.5, we use x equals 0.25 and u equals 0.25 and u equals 2.25. That's what these limits are here. So we can cancel out this x term and write this as 1/2 integral from 0.25 to 2.25 u times of the function e to the negative u, right? Just this term right here. Now, the other way you can approach this is I see an x and dx term here. So I'll just plug in x dx is equal to 1/2 du. 1/2 du. You would get the exact same thing, right? So that's a different approach you can take, right? So you might recognize that there are variable components in there. Now, if this x component wasn't here, this substitution would be a different story, because then you would have an extra 1/x component that wouldn't be able to cancel with anything else. So it's something to consider when you're doing these substitutions and whether it works in the exact form, in the clean form that we're looking at here. So you have 1/2 negative e to the negative u after the integral of e to the negative u, as we see right here. And then we apply our upper and lower limits here and here, and then we can solve for our final answer. Okay, so exact same steps. The main difference between the last two problems and this problem is this component right here. And if we graph this, we see this is the graph of each of negative u, right? So it's, I should have taken it one more step. It's canceling out this x term. So this is 1/2 each of negative u. And so in this case, we take the limits for u as 0.25 to 2.25, right? And these two integrals are exactly the same through the substitution. Okay, so for our last problem, we have cosine natural log x over x. So it looks like a lot of things are going on in this system here. So press pause and think about what substitutions you might want to apply to this problem. Think about what form of either the trig or the 1 over x or the natural log x form that you actually want to show up, and then come back and we'll walk through the process to see if it makes sense, right? If you want to, press pause, go through the u solving, the du dx relationship, and the upper and lower limits, then come back and then we'll solve the integral together. This is the graph of cosine natural log x over x from the limits 1 to 3 here. All right, so I used u equals natural log x. Okay, so that falls out right there. The fact that the derivative of this is going to be that 1 over x term is a part of the incentive there as well. Okay, so if u is equal to natural log x, do you remember what the derivative of du is, or the relationship between du and dx in this case? Well, if I just rewrote this as du dx, we can see from this integral, or the reverse of this integral, derivative of natural log would be 1 over x. So this would be du is equal to 1 over x dx. Okay. Then we need to apply the limits 1 and 3 right here. What's the natural log of 1? What's the log of 1? Well, it's going to be 0. And the natural log of 3 we'll just keep as natural log of 3, right? And then we'll plug in the calculator at the end so that we don't have any rounding errors. All right, so I have my u value, I have my du value, and then I have my upper and lower limits for u. So I'm going to do a substitution for this integral, and then we'll solve it. So here, again, I substituted dx for x du right there. I kept this x in the denominator right there, and then I substituted natural log x for u right there. Now, again, you could just do a direct substitution and recognize dx over x is right there. So I'll just do a direct substitution for du. As we see, once the x terms drop out, if we kept it in this form. But, you know, whatever makes sense to you, follow that method. It might take you one extra step as it does for me here, but I just want to make sure it's very clear what we're substituting. Then we have this upper and lower limits for the u value. Right? So lower limit 0, upper limit natural log 3. Then we take the integral of cosine u right here, and it's sine u. So sine u at natural log 3 minus sine u at u equals 0. Sine u at u equals 0 is just along the positive x-axis. So that would give you a y value of 0. So sine of natural log of 3, punch in your calculator, you get 0.89. If we graphed cosine u, we get that graph. We're familiar with that. And then the limits from 0 to natural log 3 are shown here. All right. So the process, I'll repeat one last time. See what possibly can work for substitution, right? Some term or parameter within one of the, wherever the x components are in the integral functions. And then solve, if you're testing it out, solve du dx. A lot of times things will drop out like it does right here. And that's a good indication if this u substitution is a good one or not. And then easily we can find the new upper and lower limits by plugging in here. And then we could just solve outright. Now, some people solve for the integral find sine u, they don't want to use these upper and lower limits. They re-plug in the original variable form, right? So they plug natural log x back here. So then it'll be sine natural log x. And that's a correct integral. Then you would need to change out your upper and lower limits, and you can use the upper lower limits 1 and 3 again, right? So just be aware which method you're going to use. I prefer substituting everything, including the upper and lower limits. Another way to try to keep things distinguished is when you write out the upper and lower limits, you write what variable it is for, right? So here you would write u is equal to 0, u equals natural log 3. Here you would write x equals 1 and x equals 3. Okay, so there's a couple of different, there's a more advanced substitution method that we're going to take a look at next, and that will give you a lot of expansion of what types of functions we can take the integral of.